Hello, I'm Mohammed Al Ali. I'll be talking about our work enabling efficient training of convolutional neural networks for histopathology images. As an outline, I'll give some introduction about CNN and histopathology, and I will give some background about breast cancer and the dataset that we used. Then I will explain in details our methodology and the model used. Then I will review and some results with accuracy and performance analysis. Then I will give conclusion with limitations and future work. First, we know that CNN is a powerful tool for image processing, especially medical imaging, but very deep CNN requires high computational resources. So there is a need to optimize the usage of these resources. There are two ways of optimization methods, hardware and software. Here in this work, we use software optimization. We use reducing bit width in CNN operations to reduce computational complexity and reduce the model size, which reduces the memory. Histopathology. In histopathology, this is an example of histopathologic image. In histopathology, pathologists examine these kinds of images to diagnose cancer. But why do we need to automate the process in histopathology? Because the shapes and sizes of the cancerous patterns are different. The work is difficult and takes long time and effort from pathologists. The diagnosis may vary across pathologists and by the same pathologist across time. The availability of pathologists is limited and expensive. So that's why we need to automate the process. CNN usage in histopathology. CNN have shown near-human results in histopathology image analysis, or sometimes called computational pathology. CNN provides a second opinion to pathologists. It does not replace pathologists. It just helps them to reduce their workload so that they can focus on more important cases so that they can give better diagnosis. Our target problem here, we target wearable and low energy devices. So the model is trained using high computational resources such as GPU or TPU. But the trained model is used for inference on low energy and limited power devices. So we evaluate the use of low bit width CNN on these devices. Our goal here is to design a lower bit width model that can produce comparable results to the full bit width model. So the full bit width is 32-bit. We use lower bit width 1, 2, 4, or 8 bits. As a background, we know that deep CNN, especially on very large datasets, require high resources. So there is a need to accelerate CNN to use less resources. One of the acceleration algorithms is called quantization. Quantization is defined as the process of approximating a continuous signal by a set of integer values. This technique is typically performed during inference, not during training. Our application here in this work is metastatic breast cancer. Breast cancer is the second leading cause of deaths in women in the US. Breast cancer is called metastatic when tumor cells spread from the breast region to other parts of the body through the sentinel lymph nodes. Breast cancer in this is stage number 4 of breast cancer. We use this dataset, it's called PCam dataset, Patch Camelyon dataset, histopathology images. These images are taken from breast cancer patients. The goal is to detect cancer metastasis or spread in lymph nodes. We have about 328,000 colored images of size 96 by 96. These images are divided for training, validation, and testing as so. Here we see examples of class 1 and class 0. Class 1 is metastasis, class 0 is non-metastasis. Class 1 is the tumor tissue, class 0 is the healthy tissue. Distribution is about half of the dataset in class 1 and half in class 0. Our methodology, our main goal is to train histopathology images using low bit width CNN so that this model can be used to perform inference on low energy devices. We use ResNet, which is an algorithm for training low bit width CNN. We applied ResNet algorithm using different bit widths 1, 2, 4, or 8 for weights and activation parameters on ResNet 56. We use 4 color modes. Our main idea is to convert RGB images into different representations so that to use lower energy and result in comparable testing or inference accuracy. We propose using 3 combinations of color modes beside the original RGB. We use grayscale, sparsity on grayscale, and sparsity on RGB as shown in these images, and I will explain them in details. We use random rotation for data augmentation. First color mode is RGB, which is the original color mode. We don't do anything. Every pixel is every pixel is a number between 0 and 255, where 0 is black and 255 is white. Second color mode is grayscale, which we just convert the original RGB to grayscale using this function in Torch Vision. We use a grayscale of 3 channels, 3 similar channels, because our model requires an image with 3 channels, not 1 channel. Third color mode is sparsity on RGB. We convert the RGB to a representation, as I will explain now. For each image, we convert whitish pixel to black or 0. So what is whitish pixel? Whitish pixels are those pixels that are greater than 200 on a scale of 0 to 255. We convert these whitish pixels to black to increase sparsity in the image, so that when this method is implemented on hardware, it will be more accessible and faster. We found that in this dataset, PCam dataset, there are about 20% of whitish pixels on average on all datasets. Fourth color mode is sparsity on grayscale. We take the original RGB image, we convert it to grayscale as explained before, and then we take this grayscale and we apply sparsity on it as explained in the previous slide. And here shown the final transformed image. Our main process, overall, we take the original image and then we either apply one of the preprocessing steps to convert it to any of the color modes, and then we use this color mode for training and inference on ResNet model. Our model is ResNet 56. We use ResNet 56 after applying a quantization based on the ResNet algorithm. Quantization is applied on weights and activation. W bits is for weights, represents the number of bits used for weights between convolutional layers, and activation, or A bits, represents the number of bits used for activation matrix, which is the output of the a convolutional layer. How we performed the training. Training was performed using PyTorch. We used SGD optimizer with cross entropy loss. We used 32 batch size, and we trained for 100 epochs. We started with this learning rate and goes divided by 10 every 20 epochs. We took the best parameters based on the lowest validation loss, and this model, trained model with best parameters, was used for inference. We used NVIDIA Tesla V100 GPU. The same configuration was done for all color modes. Here I show the results. You can see here different configurations, A bits, activation bits, weights bits, and for every color mode, you can see here the accuracy is different. So RGB performed best when A bit is 8 and W bit is 1. Sparsity on RGB performed best when A bit is 8 and W bits is 2. Also, you can see grayscale. We have 4 configurations give the best accuracy, and on sparsity on grayscale, when A bit is 2 and W bit is 2, performed best. You can see here that with the 3 color modes, we found best or similar accuracy with the RGB. Here, I show in details the accuracy, the true positive and true negative and false positive and false negative, and the sensitivity and specificity of every one of the best configuration in every color mode. You can see here that in grayscale we found 90% in a true positive rate, and sparsity on RGB we found 93% as true negative rate. We compare all these results with RGB original baseline with 32 by 32, which is the full bit width. You can see that all different configurations using lower bit width performed better than RGB with full bit width. In the last row, which is our baseline, we don't perform anything, no quantization, no optimization, no anything, but we use the same training parameters. For performance analysis, we analyze the number of MACs in the model. MAC, or number of MACs, is the multiply and accumulate operation, which computes the product of two numbers and then add it to an accumulator. We use this formula to find the number of MACs for every CNN layer. You can see here that RGB color mode has the highest number of MACs, but sparsity on a has the lowest number of MACs. When comparing the error rate, RGB error rate is 18% error rate for 32 by 32 configuration, but sparsity on a grayscale error rate is 17%. So the error rate differ by 1% only, but the reduction in number of MACs is about 77%. As a conclusion, we trained ResNet on low bit width quantization using DoriFaNet, and our main goal is to produce energy-efficient inference on low-power devices. We compared original RGB image configuration with 32 by 32 with the 3 color modes, and we compared 32 by 32 with lower bit width for all color modes. We found that compression methods and channel reduction would produce higher classification accuracy with using efficient energy. And here I give some limitation and future work. Limitations, because the cancerous patterns are diverse in shape and size. We found about 4,000 images with 95% whitish pixel in this dataset. Contains no tissue. We think that these images could be a source of noise in the dataset. The future work, we want to discard those images, full white images, and try another model other than ResNet, such as AlexNet or Inception. And we want to use different dataset, larger images such as TC